Good afternoon to all of you. I am Professor Nagaraju, Department of Computer Science and Engineering, YSR Engineering College of Yogavamana University, Prothutur. I was the first batch student of JNTU Anantapur, 89 to 93. So today I am going to discuss about syntax analysis. The contents are Introduction to Syntax Analysis, Construction of parse trees, left and rightmost derivations, ambiguity grammar, left recursive grammar, left factoring grammar, elimination of useless grammar, gate problems and solutions. Today I am going to discuss about these contents. So the first one is Introduction to Syntax Analysis. So syntactic analysis is the first phase of compiler. Syntactic analysis is the first phase of the compiler. A syntax analyzer or parser takes the input from a lexical analyzer in the form of token streams. A lexical analyzer or parser takes the input from a lexical analyzer in the form of token streams. So in the previous class already we have studied about how to generate the tokens and how to implement the tokens. So after implementing the tokens, we can give the stream of tokens to so that is the syntax analyzer. So the syntax analyzer, it checks whether the given input is in the correct syntax of the programming language or not. The main function of the syntax analyzer is it checks whether the given input is in the correct syntax of the programming language or not. So after that, it constructs a parse tree for checking. So it constructs parse tree for checking. We are using the different grammar, that is the regular expressions, and here is we are using context-free grammar. So for implementation of syntax analysis. So it helps you to detect all the types of syntactic errors. So in the syntactic analysis, so we can check all types of syntactic errors. So that is in the declaration of variables, or so suppose whether the expression is correct or not, whether it is in fixed notation or not. So the different kinds of syntactic errors will be, so that is detected in the syntactic analysis. It finds the position at which error has occurred. So here is in the syntax analysis, so it creates the statement number for the program, and clearly it specifies that, so in which statement, so it has been which statement at which position the error been occurred. So it clearly explains about that. So it shows clear and accurate description of the error. It shows clear and accurate description of the error. Suppose when error is displayed, the appropriate message for that error will be displayed by the syntax analyzer. The parser must reject invalid text by reporting syntactic errors. If there are any syntactic errors, so it will reject the input. So here is, for example, you see that, so that is in the programming language, we can have expressions, statements, the declaration of variables and nested statements. So but when you are using this, so that is some of the error finding examples are, so for example, you see that x is equal to within the bracket 2 plus 3 star 9 bracket close semicolon. So here is when you are given that, so here is mismatched parentheses. For example, you see that the left parenthesis only one, there are two right parentheses. So but in this case, so it displays the message mismatched parentheses. So that is here is, but this error cannot be detected by lexical analyzer. Simply so it sends a stream of tokens to the syntax analyzer. So for example, in this case, if x greater than y, x is equal to 2. So here is, but when you are using the if statement, the syntax of the if statement is if, so that is the open braces, x greater than y, close the bracket, and x is equal to 2. But here is the parentheses are missing. So when you are using third case, while x is equal to 3, do f1 function, do call the f1 function. This is invalid keyword, but here is the do is a keyword. So but is here is we are using this so as a variable or something. So that's why it will be identify error invalid keyword do. So for identifying this syntactic error for construction of this parse tree, so it uses context-free grammar. So the context-free grammar is a powerful tool for describing the syntax of programming language. The context-free grammar is a powerful tool for describing the syntax of programming languages. So I think already you have studied the context-free grammar in the theory of competition. So that's why I'm not going in depth about so the context-free grammar. But here is I will explain how to construct the parse tree by using context-free grammar. So here is so the simple definition of the context-free grammar is the context-free grammar so contains the 4 symbols. So that is V, sigma, so that is P and S, or otherwise VTPS. So what V represent, what T represent, what P represent, what S represents. So here is a set of non-terminals. So that is a V represents a set of non-terminals. So that is a sigma represent set of terminal symbols, and P represent set of productions, and S represent the starting symbol of the, so that is the grammar. So first we say that what is the non-terminal? What is the non-terminal? So the non-terminals are a set of syntactic variables. Non-terminals are a set of syntactic variables that denote a set of strings. That denote a set of strings. That is a set of non-terminals are called syntactic variables that denotes a set of strings. That means each and every non-terminal having one or more number of, so that is the strings, right? Here is these are represented with the capital letters in the context-free grammar. So these non-terminals are represented with capital letters because you have to differentiate so between the terminals and the non-terminals. A set of terminals, sigma, are a set of tokens. So that means the sigma specifies a set of tokens, so which are taken from the thing. So that is these are represented with small letters like A, B, C, etc. Non-terminals are represented with capital letters, and terminal symbols represents with small letters like A, B, C, etc. or 1, 0, etc. So for example, you see that so it is that is a binary. So that is a binary. So alphabet. So that is over sigma 0, 1, or you can represent sigma is equal to, so that is within the brackets A, B, up to Z. That means here is the alphabet over, so that is over A to Z. So the terminals are the basic symbols. That is the terminals are the basic symbols from which strings are formed. So that means these are the basic symbols. With the help of this terminal symbols only, we can form the string. The productions. Next one is the production. So, but here is when you are in the production, the productions of grammar specify in which the terminals and non-terminals can be combined to form a string. So here is based on the productions, so we can derive the, so that is the given string is accepted or not, either given string is correct, syntactically correct or not. So here is in this case productions means this production contains a set of terminals as well as non-terminals. So for example, the syntax of the production is represented with a, so suppose S can have the form of A, A. So that means here this is the one production, and another one is A can have the form of small a, capital A, or B. That means here is, so the productions always represent, so one character, one capital letter at the left side. So after that we can use the So that is can you have form, that is the test to prompt. After that, in the right side, it contains the variables either small letters or capital letters. The small letters are nothing but terminals and capital letters are nothing but a non-terminal. If it is a non-terminal in the right hand side, so we can derive and we can replace that non-terminal symbol by using terminal, so that we can generate the a string. We can generate the strings. So this is the definition of so that is the starting symbol. Yes, one of the non-terminal is designated as a starting symbol. One of the non-terminal is designated as a starting symbol. And generally, most of the cases we can use yes or e or something like this. S means that is the starting. That is sometimes you can call it as a statement. So the productions begin with this symbol and represented with the symbols. That is, the production begins with this symbol and represented with this symbol. For example, you see the S can have the form of two capital letters. So that means here is we can derive the string. So with the help of this context grammar, so we can construct the parse tree. We can construct the parse tree for verifying the syntactical structure. So that is what I mean by parse tree. A parse tree is a graphical representation of a derivation. A parse tree is a graphical representation of a derivation. That means generally we have studied trees and graphs in the data structure. This is also like same like that. So it is a convenient to see how strings are derived from the starting symbol. So already we had given, suppose when you are given the one input, the stream of input tokens, if you want to say that either those are syntactically correct or not. So first it constructs the parse tree. So that is, so based on the parse tree, that parse tree is constructed by using number of derivations. So how to achieve the derivations means the derivation, that always the, so that is the right hand side non-terminal symbol is replacing with different appropriate productions, and so that we can generate the parse tree. The start symbol of the derivation becomes the root of the parse tree. So that is any parse tree, the start symbol is that is the starting symbol represent the, so the root of the parse tree. For example, you see the main terminology of the parse tree. All leaf nodes are terminals, but here is when you see that, when you see the parse tree, all the leaf nodes are non-terminal nodes. All interior nodes are non-terminals. So that is all leaf nodes are terminals and all interior nodes are non-terminals. So in order traversal gives original input string. But here is when you are giving stream of tokens, but we can give like this: C is equal to A plus B. Here is the C is a one identifier, equal to is a one as operator, and A is a one operator, plus is A is a one operand identifier, and plus is a one operator, and B is a another operand. So that is operand means identifier, and a semicolon. So in that case, suppose here is all the programming languages accept all the, so that is only infix notation. Infix notation means, so that is operator will be in between two operand. There are some programming languages are there list, so that will be the prefix, that will take prefix notation, but I don't want to talk about Lisp programming. So here is a parse tree depicts associativity and precedency of operators. So generally, when why you have to use the parse tree means, after constructing the parse tree, it obeys the associativity and precedency of the operator. So that is the precedency means which operator will be executed first within the expression. So already we know that, already we have studied in the C programming. So suppose when you are taking the arithmetic operations, multiplication and divisions will execute, multiplication and division and modulo operator will having the same precedence, and the next one is minus and plus, that is addition and subtraction will having the same precedence. Suppose within the expression, when you find the plus and star, the first star will be executed, and the next one is the addition operation will be performing. Associativity. Associativity means how the expression will be evaluating, either from left to right or right to left. But almost all operations, so our operation associativity is so from left to right, except some operators like, so that is the increment operator, decrement operator, assignment operators. So these are so evaluated from right to left. So that means this associativity is specified that, so that is how that will be executing either from left to right or right to left. So next one is the deepest subtree is traversed first. The deepest subtree is traversed first. Deepest means suppose the tree may be contain number of levels. If there is a one small subtree, the last subtree will be executed. That means the execution should be start from so bottom to bottom to top. So here is the operator in the subtree gets precedence over the operators which is in the parent node. So for example, if operator, so suppose if the operator is in the child node, so same operator in the child node and parent node, so the first the child node operator will be executed. For example, so that is the multiplication star is so in the parent node as well as in the child node. So in that cases, first preference will be given to the child node and it will execute, right? So these are the some terminology of parse tree. So now I will explain that. So that is the construction of how we can construct the parse tree. A simple context-free grammar is, you take that, a simple context-free grammar here we are considering. E means you can say expression can have the form of expression plus expression. E means here is sometimes you can call it as a expression can have the form of expression plus expression. That is equal to generally C is equal to A plus B. So like that. So expression can have form of E can have the form of E star E. Or another one is E can have, so that is the expression, it can have the expression of that is within the bracket, we are using the expression. So like if statement, right? In the if statement, if I greater than 0 like that. So E can have the form of ID. ID means identifier or variable. So suppose these are the grammars. These are the grammars in the context-free grammar. So suppose here is we define this context-free grammar, and here is we are giving one input string ID star ID plus ID. So that means here is suppose ID means that is the identifier 1 into identifier 2 plus identifier. So that means here is suppose you can use so A into B plus C. So if you are given the string, but here is these are the stream of tokens. ID is one token, star is one token, ID is one token, star is one token, ID. That means this stream of strings received from the lexical analyzer, and next that will be parsing. So for this grammar, it will start the construction of grammar. For example, E can have the form of E plus E. That means always this is the starting symbol here itself. In the first stage, we think that E is the starting symbol, so that E can form the root. So that is here is input string is that. So here is the first we can take the E, and E is a root. So after that, so depend. So how to choose the next expression? Here is ID star ID and plus ID is there. So but if you want to take the grammar ID into ID, so there are 4 productions are there. So here is the first thing is, so the first and foremost thing of the student is you choose the correct expression for this one. But here is what we are using ID into ID. So that means here is we are using star or plus. That means if you want to use the star, we can choose this expression, or if we want to choose plus, so we can choose this expression. So that's why here is we are taken E. So within this E, so that is where star. Suppose E star E. E equal to E star. E is a root node and can have the form of E star E. So then here is we are using this context-free grammar. So here is again. So suppose here is this E can be replaced with. So suppose when you are using that, the expression is like this. This E can be. So that is the replaced with the productions of E can have the form of E plus E. Why? Because our statement is, so that is ID1 ID star ID plus ID. So that's why here is the star is there, and next this is replacing and E plus E. So the second production is replacing the E. So after that you see that, so here is E is replaced with ID. Then you go to this place. Suppose here is, so E is equal to ID. That means here is, this is also one product. Appropriate productions you have to choose to find whether it is a correct or not. So that's why here is the E is there, ID identifier we are choosing. So after that, that will comes to this place, and here is, you see that ID. Again we are taking the ID of this, and for this E it is replaced with the production of ID. So now we have constructed the parse tree. This is the parse tree. You see that E can have the form of E star E. We are choosing this grammar, and first we constructed the parse tree. So suppose here is the root node is the starting symbol. So after that, an appropriate selected production can be replacing the root node. So E star E, and the next ID, and next E, that is equal to E plus ID or something. So for example, so if you have taken that, here is the first one is A into ID into ID plus ID. For example, if you have taken ID plus ID star ID, if you have taken in the reverse case, so first one is, we can choose this one as a starting node. So suppose here is the E plus E. After that we can identify E. So suppose here is suppose identify, and here is we can replace the plus, and next we can get the value of this. For example, if we take this value, so suppose in the reduction process, when you see that here is, suppose if I taken this ID is 2, this ID is 3, and this ID is 4. But in that case, you see that first this will be, this is the deepest, that is the, so the deepest subtree will be executed as per the rules. So then here is, so the 3 plus 2, that is the 3 plus 2 is equal to 5. Here is, that will comes to 5. That means this tree is reduced, and here is a 4 is ID, and E is replaced with the 4, and the next 4 into 5, so that is equal to 20. It will evaluate, that is equal to 20 of this. That expression will be evaluating like this, right? But here is, so what are the concept I explained there? So the first, that is the starting symbol is the root node. The productions are replacing. So that is all the terminal symbols are. So that is the, so that is all the leaf nodes are terminal symbols. You see that ID is a terminal, star is a terminal, ID is a terminal, star, that is the operator, and ID. So all the internal nodes, you see that 1, 2, 3, 4, 5, all these are the, so representing capital letters, that is the non-terminal nodes. But here is, when you are using the parse tree, so that is, you are constructing the parse tree. But how to construct the parse tree? How to choose the productions, right? So this is the very important. Suppose, for example, when you see this, so derivations, that is how to derive the tree. So that is the deriving like this. But here is, suppose I have taken like this. But as a human being, we can choose this one. Suppose if we, first we are chosen, because first star is there. That's why I choose this one. But how the compiler will identify, how the parse tree can execute. So for that purpose, we can use some of the derivations. That is, suppose a derivation. What do you mean by derivation? Derivation is basically a sequence of production rules. Derivation is basically a sequence of production rules to get the input string. So here is, you see that for getting this input ID into ID plus ID, so here is, we deriving the parse tree. We derive this parse tree. Right? So that means that is the derivation. With this parse tree, so we got the input string. Suppose if the input string is different, the parse tree is different. That means the tree is constructed, so the based on the given input string. So that's why here is you can say that derivation of tree means derivation is basically a sequence of production rules to get the input stream. During the parse tree construction, two decisions must be taken sentential form for input. So suppose during the construction of parse tree, so we have to make two decisions on the sentential form of the input. Depending upon the input sentence only, we have to construct the parse tree. We have to construct the parse tree. So that is, first one is which non-terminal should be replaced. Which non-terminal should be replaced. This is very, very important. So you have to identify which non-terminal should be replaced. For example, here is you see that, so here is for this one, here is a one non-terminal, 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 so here is the non-terminal, non-terminal. So either first one is either you have to replace ID, suppose here is taken this one, ID into ID. But these are two productions are there, but which one we have to choose is a very, very important. After that, here is we are taking, that is here is we are chosen this one ID for this non-terminal. So which value you have to represent? Here is directly we are taking the ID, and here is again we are expanding E with E plus E. That means this selection is a very, very important while we are deriving the tree. So that is the first one. So second one is which production should be replaced. Which production should be replaced? Already I explained that. So which one should be replaced? So that means while you are constructing the parse tree, so if you keep these two in your mind, then it is very easy to draw the parse tree. Blindly you can draw the parse tree. But if you are good at, so that is the selection of non-terminal, so the production further. Suppose the same non-terminal may be having any number of productions. For example, you see that E is a non-terminal, so there are 1, 2, 3. So that is here is, suppose here is when you see that here is the E is a production, that will be 1, 2, 3, 4. So productions are there. So which production you have to choose? That is also very, very important. That means in the derivation we should remember these two. There are two options to choose non-terminal. There are two options choose non-terminal to be replaced with the production rules. But here is one is the leftmost derivation and another one is the rightmost derivation. As a human being, so we can choose any non-terminal symbol. But when computer, you have to give the instructions. Either you have to read the non-terminal symbols from left to right or from right to left. So depending upon that, it has to replace this. So now I will explain that leftmost derivation and rightmost derivation. What is the leftmost derivation? So I understood that what is the parse tree, what are the terminology of the parse tree, and what is the context grammar, and how to construct the parse tree. So if you want to construct the tree, so that is what derivations you have to use. Here is we are using two derivations. One is the leftmost derivation and another one is the rightmost derivation. First you see that, so suppose in the derivation you can see that. So suppose same, already the same thing I have taken E, can you have the form of E star E? So we can call it as a derivation. First this is thing and here is a E star E and E, so suppose this E is replaced, this E is replaced with E plus I, and the next one is E is equal to ID, this ID is replaced with ID and this ID is replaced with this E, and so this E is this non-terminal is replaced with this ID. So that means here is the first we are taking the string, so that is the starting symbol, we are choosing the product E star E because the input is ID star ID plus ID. So after that, so then here is we are replacing the second E with the productions of E plus E. So then after that, so we are initializing E is replaced with ID and this E is also replaced with ID, and this ID, that means this is the thing. This is derivation. Already I explained, right? But this derivation, the leftmost derivation. What do you mean by leftmost derivation? If the sentential form of an input is scanned and replaced from left to right, it is called leftmost derivation. If the sentential form of an input is scanned and replaced from left to right, it is called leftmost derivation. That means here is evaluation should be from left to right, either scanning or replacing. The sentential form derived by the leftmost derivation is called as a left sentential form. The sentential form derived by the leftmost derivation is called as a left sentential form or left sentential form. For example, you see that how to construct that. Suppose this is the, so for example, this is the starting symbol in the previous grammar already. So just you note it down that grammars, because throughout this lecture I can use those grammars, right? So you take that starting symbol of that grammar is, the context free grammar is E. But the same thing I am writing. So then E star E. So for example, E can have the form of E star E. So E star E. But when you are using the E star E, so then first thing is we can take this one as the root node, and this is the left child and this is right child. So because here is the evaluation should be from left to right. So first here is the two non-terminal symbols are there. In the leftmost derivation, we can consider, we can replace this. We can replace this with the terminal symbols or any other productions until we get the terminal symbol. So after that, next one, left to right. So next you see that, not this one, okay. So this is the rightmost derivation. So for example, yeah, you see that. But here is, but when you are using that, here is, forget about this. So here is, you see that A and E star E plus I. So then here is, you are taking that, and here is, just you take that is E is equal to ID, and this E is replaced with E plus ID. So the evaluation should be like this. Suppose you see that first ID, next second ID, and next third ID. So the evaluation is from left to right. This is called leftmost derivation. This is called leftmost derivation. For example, you see the graph. So that is, now you see the leftmost derivation for this tree is. So just I have understood that. So previously I have drawn the derivation like this. For example, so that is the first you have taken the grammar, but it is a right intentional. Just I implemented this. But now, how to construct the leftmost derivation for this derivation? So the first one is you take the root. So here is we are taking the root of this. After that, so in the leftmost derivation, in between these two, we can take the leftmost E. So then that will comes to E, leftmost E, and the next to rightmost. So then here is the first E. You see that is the leftmost E, and the next that is next to star, and next to E. It starts with from left to right. So after that, here is the two E's are there. That is the two non-terminal E's. So then, in this case, in the leftmost will be replacing first. You see that leftmost is ID. It replacing leftmost is ID. After completion of this, next that will comes to this place. You see that here is also it follows the E, and the next that is the star plus, and the next that is the E, and the next that is ID, and the next that is ID. So now you see that the construction of leftmost derivation. I understood that. So again I will explain this. You see that in the leftmost derivation, the leftmost non-terminal should be replaced with its productions. So that is, so until to reach the terminal node. After that, next, that is the scanning will be from left to right. So here is in this derivation, first you take the root. So after that, so that is the left derivation. Next that is the right derivation. Here is the E star, and the next E. Or next that is this one is the first this one. So next E, next plus, and next E. Next this is not directly, it will not displaying that ID. Here is that will be displaying ID, and next this is ID. So this is the leftmost derivation. For the same thing, another one is the rightmost derivation. It is so quite opposite to the leftmost. Here is if we scan and replace the input with production rules from left to right, it is no from right to left. Sorry, from right to left, it is known as rightmost derivation. I think you understood the leftmost derivation, right? This is quite opposite to this one. Here is the scanning and replacing of the input with production rules from right to left. It is known as a rightmost derivation. That means the right side last non-terminal we can replace with its productions. The sentential form derived from the rightmost derivation is called as a right sentential form. For example, you see that rightmost derivation. So that is everything is animation. Just you clearly observe that. Clearly you can understand. So that is the graphical representation is more attractive, more understandable than documentation. So that's why I took a lot of time and I prepared these slides, right? So that is, you see that rightmost derivation. So that is with the help of my students I developed this one. So that is here is E can have the form of E star E. That is E star E. So then here is derivation. You see the rightmost derivation. So then here is we are given to rightmost derivation. For example, in this case, the last case we have taken this, but here is we are taking the rightmost derivation ID. Here is instead of taking it, so that is the plus, here is we are taken star. So next this E is replaced with E plus E. This is replaced with E plus E. After that this E is replaced. That is the right, not from left side. This is replaced with ID and this last one is this one. So this is the rightmost derivation. So once again you see that. So this is the root and here is the first derivation we are writing. Here is in the leftmost derivation we have to replace this non-terminal with its production, but in the rightmost we are replacing this non-terminal. Suppose here is the first one is ID and next this is replaced with, because here is E is replacing with E plus I because for getting the things. So next here is in between these two, which one you have to replace? Either this E or this E. You have to replace this E because this is the right. So that is the right and the next this one is ID. So then after that the evaluation should be calculated from up to this place. For example, suppose in the evaluation, so then we can use, so that is you can use like this. Suppose here is if you are given 2, 3 and 4. Suppose when you are given like this, but actually here it takes 2 plus 3. 2 plus 3 is a 5 and that is here is that will taking the 2 and this is 3 and 2 plus 3 is a 5 and the next one is, so here is a 4 and here is 9. You can get the answer is 9. So but in the previous class you got different, right? But here is the leftmost derivation and rightmost derivation. But here is how much value you got. So that is the only you got 9. But in the leftmost derivation, so how much value you got? I think somewhere no. So that means suppose when you are using the leftmost derivation, so we can get a different value. So that is the first star will be performing or like this. But in between these two, either leftmost, you can use either leftmost derivation or you can give the rightmost derivation. That means every parse tree must contain either leftmost, you can derive either leftmost derivation or rightmost derivation, depending upon the input string. But here is when we are using this tree, so that is the parse tree, you remember that here is we got, so that is the 2. But here is suppose if I are given, so expression is 2 plus 5 into, 2 plus 3 into 4 is equal to how much? According to computer, highest priority will be given to star. So then 3 into 4 is a 12. 12 plus 2 is 14. Here is we are getting 14. But when you are using this is from so that is the right to left. So suppose here is taking that is the suppose if you are taken that, but here is in this case 2 plus 3 we are performing what? 2 plus 3 is equal to 5. So 5 into sorry here is the 5 into not 9. So 5 into this one is the 20. Where is they getting? So that is the 5. 5 into 4, 20. Here is also 2 plus 3, 5. 5 into 4, 20. Or here is also 3 into, sorry, 4 into 3 in the right sentential. 4 into 3 means, suppose, according to mathematics, 4 into 3. So then here is, we can see that 12. So 12 plus 2, 14. But in this case, but suppose when you are going to that leftmost derivation, so we can get 2 plus 3 that is equal to 5. 5 into 2, 20 you are getting. So which answer is correct? Which answer is correct according to rules? So that means in the rightmost derivation you got 20. In the leftmost derivation you got 14. You got 14 of this. Or suppose in this case here is 2 plus 3, 5 and 3. So but here is which one is the correct? There is ambiguity is occurred. There is ambiguity is occurred, right? Understood that? So that means here is ambiguity is occurred. So but when ambiguity is occurred, so but when ambiguity is occurred, if for the single input value, if you construct more than one parse tree, if the any single input string, it has more than one parse tree or more than one only left subtrees or more than one right subtrees, then that grammar is called ambiguity grammar. I think clearly you understood that. So here is the rightmost and the leftmost. But when you are evaluating with the leftmost and rightmost, so you are getting 14 and there we are getting 20. So that is in the leftmost grammar we are getting, so we are getting 14 and in the rightmost we are getting 20. So then 40 and 20 means, suppose here is, so ambiguity is there. This is ambiguous. But what do you mean ambiguous? For some string there exists more than one parse tree or more than one leftmost derivation or more than one rightmost derivation. The tree is called as a ambiguous tree. So that is for some existing string there is a more than one parse tree. If there is more than one parse tree or more than one left subtree or more than one right subtree, then the tree is called ambiguous. For example, the same thing here is just only I have taken this. So for example, you see that, but in the previous case I have taken id into id plus, but here is we have taken id plus id into id. So for this one we are using this grammar. By using this context free grammar, so we can derive two trees. For the same id we can derive two trees. So that is here is e, the root node, that is the e is equal to e plus e, and this is called, so that is the id, and here is an e star, this is the leftmost derivation, right? This is called the leftmost derivation, e star e id and id, and here is also you take that is the id, and here is we are taking this one id e star e root node e star e. So this is the rightmost derivation. First that will be replacing id, rightmost e, next rightmost e, next rightmost e. For the same grammar, for the same given input string, for the same, so given input string, for a given input string, we got two trees. For example, here is the same application you take 2, that is the plus 3 into, or I took 5. So that if we want to evaluate this expression, so the first here is we can use the id. So then here is the first one is we can use id is 2, right? Sorry, here is the first it will take, that is the deepest node, that is equal to this is 3, and this is 5. So first deepest node will be H. 3 into 5. So that is the, here this is replacing with 5 and this is replacing with 3. So then here is, so 3 into 5, that is equal to 15. That is equal to 15. After that we will take 2 and here is E is replaced with 3. So that is the plus. So 15 plus 2, that is equal to 17. You got, answer is 17. And here is the same thing, you see the deepest, that is the deepest subtree will execute first. So first you see that ID plus ID. ID is, suppose you have taken 2 and next 3. Then 2 is replacing that E and 3 is replacing, 3 is replacing this E. So then here is 2 plus 3, that is equal to, you are getting 5. You are getting 5. And next this ID is 5, right? This ID is 5. So then here is, this is replacing 5. Then 5 into 5, that is 5 into 5 is 25. Got 5 into 5 is equal to 25, right? So now you see that here is, so in one tree, when you are constructing one tree, we got result is 17. In one tree, suppose in the rightmost derivation, so that is we got tree is, so that is 17, and it is in the leftmost derivation, so that is we got 25, right? But in this case, which one is the correct answer? There is ambiguity occur. So that's why we can call this is the ambiguous. This is ambiguous, right? So that means I have understood the definition of that ambiguity. That is, for some string there exists more than one parse tree, or more than one leftmost derivation, or more than one rightmost derivation, then the tree is called ambiguous tree. So for this grammar, suppose when you are using this, so for this grammar, so that is we are having, so that is the ID and so ID plus ID star ID. So then we are getting two different values. So ambiguity is there. If ambiguity is there, so that definitely the computer will not make decision. You can't get correct results. But here is some of the trees, you see that ambiguous trees. So suppose this ambiguity, left derivation, right derivation, these are very, very important for gate, right? So here is I am explaining the theory means, so that this is also the problems I am explaining, right? So here is an ambiguous tree. For example, you construct the grammar. Suppose when you take the context-free grammar here, so suppose when you are taken, so G is equal to, grammar G is equal to, so three non-terminal symbols, that is S, comma, A, comma, B. These three capital letters are non-terminal, and sigma, that is our alphabet is A, comma, B, and P is the production, set of productions, S is the starting symbol, where the production set P is given by, so S can have the form of AB, capital S, B, or A, capital A, B, or A. Or A is equal to, A can have the form of A, capital A, B, or B, capital S. Prove that the G is an ambiguous grammar for given input string AB and AB. Here is, we are given input string is AB, AB. Here is given input string is AB and AB. So first you see that solution. There are two solutions are there. First you take the yes. So that is the starting symbol. First I will consider this production and I will solve the problem. Suppose AB capital SB. But here is AB capital SB, and here is, this can be replaced S. S can be having three productions, that is the AB, SB, A capital AB and S. But here is the first AB is there, and next what symbol you have to come? It has to come A. So that's why it will searching the symbol which is start with the A. Suppose here is the A, and the next two productions are there. So here is also there, next two other productions are there, A is there. So then here is, S is replacing with A. This capital S is replacing with A. Then we can use S is equal to AB. That means here is the string as produced. That means when I am taking the first production I produce that string. That is, string is accepted. Syntactically, it is correct. Or second, the same thing, I take the second production, A, capital A, B. So suppose here is the second parse tree, a derivation, you can it is a derivation, but when you draw it, it is a parse tree. So suppose here is the S, you can have the form of A, capital A and B. S, A, capital B. So here is S is equal to, so then we are having A, B. So suppose here is S, A, B. So production A, here is taken A, B, and here is, so two, for here is A, suppose A, capital A, B. Here is A, capital A, B. Here is a capital A means it is a non-terminal. So the A is replaced with the any one of its productions. But here is the A, you can have the two productions. Capital A, B or B, S. So then here is the A is there and next suppose B is not there. So then here is BS. This is A, capital A is replaced with the BS value. Here is, so suppose here is, so capital A is replacing with the BS value. Capital A is replacing with the BS value. And after that, and here is, so then string will come like this, A, B, S, B, A, B, S, B, S. Again, that means A, apply A for BS. Our next S is equal to, S is replaced with A, and then we can get AB and AB. So that means for the given string input AB, so here is the two productions are there. So that is the two, so that is the syntax trees are available. So that's why we can say that it is a ambiguous grammar. So that it is called as a ambiguous grammar. For this production, we generate one tree. For this production, we can generate another tree. So that's why I have understood that it is a ambiguous grammar. So for this one, so suppose you take another grammar, I understood that here is only I have taken the derivations and productions. But here you see that, so consider the grammar G is equal to S, that is a set of non-terminal symbols are only one, that is the capital S. So that is the sigma is, that is the alphabets X, Y, plus, star, and P is the production, S is the starting symbol. Where production consists of, S can have the form of S plus S or S star S or X or Y. Is it ambiguous grammar for the context-free grammar? So that is X plus X star Y. X plus X star Y. So that is the previously I explained that. So for this one, first I will take the first, so that is the first rule. Suppose for example, when you are taking this, so first one is, I am taking the first production. Here is I am taking first production. Either it is possible to derive the string or not, I will verify. So here is I am constructing that. So S can have the form, so that is a S plus S. We have taken S is equal to S plus S. And here is S is that is the terminal, S is replaced with the non-terminal production X. After that, here is X star Y is there. X star Y means we are selecting another S star S. Then S is replaced with S star S, but here is I did not write. So then here is you can write like this, for example. So that is here is, so somewhere you write it, so that is a S, and here is also you can write S. So that is after that, so then you see that. So after that you can use the X, and here is, or something like X, or another one is, suppose here is you can use the Y like this, Y productions. But when you are using the X and the Y and the S and the S, so then you got the string is like this, X of this. For the same thing, but here is the second case I took this one, S into S. So the same thing, S or S, here is I have taken this S. So S is replaced with X, and here is X, and here is the Y. But when you are evaluating this, but you got the X into X, X into X, X plus XY star. So for this grammar, so there are two trees are there. There are two trees. So that's why this is also ambiguous grammar. So you consider the next example. So here is I have explained 4 examples, right? So because So that is, if you clearly understand these examples, so in the gate easily you can answer for this, because it is, the entire thing is the mathematics and it's a very interesting subject. But only thing is you must have some patience to listen. That is the only thing. Now, if you have patience, definitely you can learn these subjects. So definitely you can gain the, so 10 to 15% of marks in the gate, because so combined language compiler design or theory of computation. This is the most important among all the subjects for the gate, for any other competitive examination. Consider the grammar G is equal to, so that is the set of non-terminal symbols E, so that is alphabet A comma B, P, S, where production consists of E is equal to E plus E, or, so that is the A. Here is we can use the E, S, R, A. So that is E can have the form of E plus E or A. So that the grammar is ambiguous. W is equal to A plus A plus A plus. The same thing. We can take that is the A plus, and this is replacing plus A, we got this. So for the right, this is the leftmost derivation, this is the rightmost derivation. E is equal to E plus E, and this E is replaced with A, and this E plus E, A and A, that is equal to, again you got A plus A plus A. That means here is you got two more, one is the leftmost and another one is the rightmost. So then this grammar is also a ambiguous grammar, right? So another grammar you consider this. So consider the grammar G is having the following productions. I think so in the previous gate question paper, so I saw this one. So suppose, so there is many times they are given this one. So that is, here is S is equal to A capital S, B capital S, or B capital S, A capital S, A, or B, A, and epsilon. So that the grammar is ambiguous for AB and AB. So you construct a grammar for this. So try for it. Then again, first I am taking this, first S is the starting symbol, root node. So I consider this AS, ASB, so that is production of first production, and here is, so that is here is AB, depending upon this application, first we are taking A, B, A, B, after that, so that is no, is, suppose if it is A, and here you can replace, but here is, there is no other character, we are replacing it with last function, that is the epsilon, that is we are replacing it with the epsilon operator. So the same thing, suppose you see that S, you consider the second production, so ASB, sorry, so the same ASB, that is first production, ASBS, and next this S is replacing, but here this S is replacing B and A, but this S is replacing BSAS, the second production, and here is S is replaced with epsilon, S is replaced with epsilon, here is S is replaced with epsilon. So then we can have AB. So then here is epsilon can be so deleted from the expressions. That's why. So here is also two grammars are there, left subtree and right subtree. So this is also ambiguous grammar. I have understood that. I hope you understood very clearly about that ambiguous grammar. If you have any doubts, you can post the queries. So then advantages with ambiguity. So there is a, so but actually when you are using the ambiguity, there is a drawback is there. Generally there is a one drawback. So but here is sometimes the advantage with there are some advantages with ambiguity. For example, you can see that while we are sitting in the home, so that was the problem in the previous days. But now, so that is when you are sitting in, because of that corona, when you are sitting in the room, we are saving the country, we are serving the country. But suppose the previous, before corona, when you are sitting in the room, in the house, they call that, so they are busy people. So now, when you are sitting in the house without going out, so then we are saving the Indian people like that. So the same thing here is also, the ambiguity also having some advantages. So that is a certain type of ambiguous grammars are quite useful in specification and implementation of the language. So sometimes suppose the ambiguous grammar is also so very useful, because here is the smallest product. That is, our intention is what? We have to reduce the space complexity. We have to increase the execution speed of the program. So in that case, for the same grammar, if there are more number of trees are there, you see that here is this is the one tree and this is another tree. So what is the time complexity of this tree? Either if it is a binary tree or any tree, so log n base 2. Suppose log n base 2. Suppose when you are taking log n base 2. But in that cases, if the n value number of levels are increasing, so that is its time complexity will be increased and the space is also wasted. So that's why with the help of this ambiguous grammar, we can construct different types of trees. Among those, we can choose the optimal solution. That is the main advantages of using ambiguous grammar, but it is not always correct, right? So for example, that is a grammar can be used. So second one is that is code optimization. Already I explained that. If you want to reduce the program size, so then for the code optimization, we can use the ambiguity of these two. So these are the advantages, but only two advantages are there, but there are so many drawbacks are there, but we can't make the decision on the statement. So that's why, but how to handle the ambiguity, how to handle the ambiguity, how to handle the ambiguity of the grammar. Ambiguity can be handled in several ways. Ambiguity can be handled in several ways. One is the rewrite the grammar with the cleanest way. First one is whatever the grammar they are given, so then you rewrite that grammar with the cleanest way. Clearly you have to rewrite the new grammar for that. That is the new version of that grammar. So second one is enforce associativity and precedency of the operators. So already I explained that associativity and precedency. So precedency means, so that is the which operator will execute first. Associativity means either the operations will be executed from left to right or right to left. So that is the associativity. So for example, so for this one simple example I will explain. So suppose here is, so suppose you know the roots of a quadratic equation. So suppose ax square plus bx plus c is equal to 0. Suppose if you are given r is equal to, so that is plus or minus, so that is the b plus 0 or something like this. Suppose when you are taking square root 0 means, suppose here is a b by 2a, b by 2 into a we can get. In what case we can get linear equations? So if the discriminant value is 0, then we can get the b by 2a. So suppose when you are using the b by 2a, here is when you are using this. So if you are given, so b is equal to 4, if I are given b is equal to 4 and next a is equal to 2, input I have taken a is equal to 2 and b is equal to 4. So but when you are using this, for example, here is, so that is a 4 by 2 into 2 into 2. So here is actually according to mathematics, suppose when you are taking that, according to mathematics we can get the -1 and -1. That is generally we can say that 4 by 4 is equal to 1. So but here is when you are executing this, here is instead of getting that you can get the 4, we can get value is 4. But according to mathematics it is wrong. But you have to get the answer is -1. Why you are getting means that is the precedency of the operator and associativity. Associativity means the evaluation should be from this experiment left to right. The evaluation should be from left to right. That means 4 by 2. 4 by 2 is equal to 2 into 2. So then you are getting 4. It is correct mathematically. Suppose, so in this case, for example, but the same thing, precedency of that operator, according to precedency, first this will be executing and next this will be executing. So that, but instead of getting 1, so we are getting 1, so -4. So that is the answer is wrong. So how to eliminate this? So suppose here is we can write 4 by, so that is within the bracket, so that is the 2 into 2. You take the 2 into 2. But when you are using 2 into 2, so that is highest priority will be given to the parentheses. So 2 into 2 means that is the 4 that will be calculating first. After that 4 by 4 is equal to 1. So then this is the correct answer. But in the computer, most of the students, in the while they are writing the quadratic equation, if they are writing the code R is equal to B by 2 into A, but according to syntax it is correct. So, but according to associativity and precedency, so then this is wrong. But here is we can get the answer is 1. I understood that. So then here is, but whenever you are using that expression, evaluation of that expression, so you should provide the associativity and precedency of that operators based on that precedency, so that we can eliminate the ambiguous grammar. Handling the ambiguity. First one is rewriting the grammar to eliminate the ambiguity. Rewrite the grammar to eliminate the ambiguity. So that is disambiguity rules are applied for getting only one parse tree for each sentence. When you are given the input sentence, for that sentence and input sentence, if only one parse tree is there, it is correct. If more than one parse trees are there, ambiguity is occurred. So that's why here is we can use some disambiguate rules. Based on that, we can convert the ambiguity grammar into disambiguity grammar. Therefore, the overall language specification become unambiguous. For example, that is, here is another case we can use the design LR parsers. Later I will explain in depth about LR parser that follow the same ambiguity resolution choices. So here is, for example, you see that already I explained that this grammar is ambiguous. This grammar is ambiguous for given input A plus ID plus ID into ID. That means we can solve that problem, left derivation and right derivation. So that's why here is this grammar is ambiguous. The grammar is ambiguous because it does not specify the associativity and precedency of the operator. Because here is in one tree we are evaluating the plus first, and in another tree we are evaluating star plus. So, but there is no precedency. So that's where ambiguity is there. So that is how to avoid this ambiguity. For example, so in that case you see that, but the same thing, just this grammar is replacing with the rewriting the grammar. Rewriting means without violating the rules and without changing the meaning, we are adding some more labels or something like this. So suppose you see that, so that is the first we have taken E is equal, E can have the form of E plus E. So that second E is replaced with T. Second E is replaced with T. So then here is E is equal to T. So when E is equal to T means, so next one is E can have the form of E star E. But here is the E is equal to T now. So then, so E is replaced with T. So T can have the form of T star F. We are taking E is replacing with another F. So then T is equal to F. F is equal to the same thing. So that E and F is equal to N. So this is unambiguous grammar. So for this one, when you draw the tree, so definitely you can get only one tree. Definitely, I understood that how to avoid the ambiguous. So that is, you take the ambiguous grammar. So you rewrite that ambiguous grammar by adding some non-terminal or by removing some non-terminals or productions. So E can have the form of E plus E. So here is instead of taking E plus E, so that is the E is replaced with T, and here is extra production, E is T, and here is also T is equal to T star F. But here is E can have the form of E star E. E star E is replaced with T and F. So that is here is, so T F, that is the E. Here is the T is replacing the E and F is also replacing E. That's why T is equal to F. F is equal to, within the bracket, we are using FD of this. For this one, so that is when we are drawing the grammar, so I forgot that. So that is when you draw the tree, definitely you can get the non-ambiguity tree. So second one is operator precedence on both the sides. So suppose here is A plus B, left associativity, some operators are having the right associativity. So that is the thing. Precedency means suppose if you are given that A plus 5 star 2. So that is the interpretation because of two different. A plus 5 star 2. Suppose in this case, so if you are given that, suppose if A is equal to, if you are given 2, then here is 2 plus, first this will be executing because highest priority precedency will be given to brackets, that is a 2. 2 plus 5 is 7. 7 into 2, 7 into 2, that is equal to 14. We are getting 7 into 2 is equal to 14. And here is the first this will be executing because here is the bracket is there. So then 5 into 2 means, so that is the 10. So that is the 10 plus 2, that is equal to 12. You are getting answer is 12. So this is the precedency of the operators. So suppose depending upon that, so either which operators you are using, suppose, so how to combine them, suppose in the quadratic equation, previous case also, b by 2 into a, instead of writing b by 2 into a, you write b by within the bracket 2 into a, so then you can get the correct results. So that is the precedency of the operator. The precedence determines the correct interpretation. So that is in the C program, that's why while you are studying the operators, so then you see that what operators evaluate from left to right and right to left. Our next one is what is the precedence? If there are more than one operator in the expression, which operator will be executed first? In the beginning class, I explained some of the C programming. So for this precedency and associativity, based on the precedency and associativity, so then you can get the different values. If you are good at knowing the precedency and associativity of operators, so then you will become a good in the any programming language. But here is in the constructor that rules are defined by using the precedency and the associativity of the operators. So here is the same thing, that is later I will explain that. But here is suppose elimination ambiguity grammar. So that is the if statement grammars of that is the so suppose this is the left that is the ambiguity grammar, right? So understood that. So positive derivation, leftmost derivation, rightmost derivation, and the next ambiguous grammar. So but while you are using the next one is with the left recursion grammar. So that is the left recursion grammar. Suppose when you are using that right recursion and left recursion. So recursion means, so for example, so if suppose if the tree, suppose when you are constructing the parse tree, but in the data structure we can study about that as a left skew tree or right skew tree, left skew tree or right skew tree. So for example today, so in the data structure, so madam has explained quicksort. The quicksort, so suppose if you are given the elements, all the elements are in the ascending order, you can get the worst case time complexity. That means, but when you construct the tree, so we can get the rightmost tree. We can get the rightmost tree, only single line. Or suppose if you are given the elements are in the descending order, so you can construct the leftmost derivation. But for the leftmost derivation, for the rightmost derivation, so that is equal to linear time complexity, order of n or order of n square. So suppose in the worst case, then we can get the order of n square in the quicksort. But in the same way, here is also, suppose when you are using the leftmost derivation or rightmost derivation, there is a chances of fall in infinite loop. Sometimes you can see that the program will be fallen in infinite loop. So that is called recursion. For example, how do you say that left recursion? So a grammar is a left recursion if it has a non-terminal a such that there is a derivation a tends to a of capital A of small a, capital A of small a. So that is the grammar is left recursive if a has a non-terminal a such that that there is a derivation, so a tends to a of a. But here is if you want to derive this, for example, always it will be tree will be constructing. Let us show the tree. Left recursive grammar is considered to be problematic situation for top-down parsers. In the next class, I will explain the top-down parsers. So, but when we are constructing the top-down parsers for syntactic analysis, syntactic parse tree, so that is the left recursion is the problem. So that's why you have to eliminate the left recursion. So here you see that top-down parsers start parsing from the left to start symbol, which itself is a non-terminal. So here is the non-terminal, and the next, so that it will be repeated. So always left terminal replacing a. So then here is, so then it will be fall simply in the finite loop. So that is a infinite loop. So for example, so suppose a can have the form of ab or something like this. You see the grammar is an example of indirect left recursion. So for the previous case, here is we have taken a extends to a capital small a. So for this one, here is an a, so can have the form of a alpha. Here is the a alpha is the root. Then the a is replaced with another a alpha. Again that will comes to this a alpha. Here is the alpha and capital A. Again this a is replacing with, so that is the alpha and capital A. Alpha capital A. This will be simply, this can fall in infinite loop. So this is called left recursive. This is called left recursive. So that means here is you never find the answer. You never find the answer because, so the A is, there is no other form of A. So that's why A can be always replaced with A alpha. So suppose A and alpha or something. So this is called leftmost recursive function. And rightmost recursive function means, so alpha and A, you can take alpha A. So then automatically you can get the reverse string for that. So this is called left recursion and right recursion. In the top, so that is the top-down parsers. That suppose when you are reading the left recursion or right recursions, or ambiguity are the problems. In the next class, I will explain the top-down parsers. So that is at that time. So I don't want to explain all these things, right? For example, so here is I am explaining this. Suppose when eliminating all this grammar, that is the left recursion, right recursion, left factoring, and ambiguous. So then only it is possible to draw the top-down parsers, right? So that is here is how to eliminate the left recursion or right recursion. Suppose the elimination. Suppose when you get the formula like this. Suppose if the string is like this, A extends to capital A of A. This is simply fall in infinite loop. So, but here is how to eliminate this one. What is the procedure to eliminate? For example, the left recursion can be eliminated by using this grammar. For example, so in that case, if we have taken the rule is like this, A can have form of capital A alpha or beta. But when you are using the form, so this will be always replacing with A or something. We may be replace it with the same. This is the same procedure. You clearly observe that. So because only the statement you have to remember for elimination of left recursion. Because in the gate examinations, ambiguity, left recursion, left factoring. So these are very, very, very important, right? A can have the form of, so that is the beta and alpha. That means we are rewriting this. A can have the form of capital A alpha slash RB. The same thing can be rewriting like this. So for eliminating this left recursion. So capital A can have the form of beta and A slash. For this beta we can write A slash. So but here this A slash can be given the productions of reverse of this A alpha. That is A slash. That is alpha A slash or epsilon. A can have the A slash can have the form of alpha A slash epsilon. Here is the epsilon will come. Suppose sometimes if the sentence is not connected, then we can use the epsilon. So that is the, we can write it. This form can be written like this, so that we can eliminate the left recursion. So you see the example of that left recursion. Left recursion grammar contains the following kinds of this. For example, you see that A can have the form of A alpha 1 or A alpha 2 or A alpha 3 dash dash up to n, or A alpha n, or beta 1, beta 2, beta 3 are up to n. So if this is, when the form is like this, So there is a chances of falling in the left recursion because so suppose in this case capital A is there, but there is no productions for this A. So that's why here is entire thing can be written like this. So A can have the form of, so that is for this terminal symbol beta. So beta A slash beta 2 A slash beta 2 A slash up to N. So here is you can use the A slash, and the A slash can be replacing. Here is alpha 1 A slash, alpha 2 A slash, alpha 3 A slash dash dash up to this. So these two formulas you remember how to eliminate the recursive functions. So that is you have to remember these two, how to eliminate the recursive function. For example, for the given grammar, here this is the left recursion. You see that is suffering from the left recursion because the capital immediately the capital E is there. So the second one here is also, this is also suffering. T can have the form of T star F. So it is also left because suffering from the left recursion. But how to eliminate this left recursion? For example, you see that, so that is it's a E, capital E, capital E, capital T, capital T. But this is in the form of A alpha or beta. This is in the form of A alpha beta. So A alpha beta means we can take E slash, we can take that is the A is equal to, can have the form of A alpha beta. So we can consider this expression E is a A according to the previous statement. So we are considering E is equal to A, and the next latter, this is the terminal symbol plus, we remove that, we can keep as it is, and T is replacing with alpha or T is. So suppose this statement and this statement is similar. So the similar means how do you write? So then here is we can write the same sentence, we can rewrite it. So that is E tends to T E slash. So there we have written A is equal to, suppose A is equal to, so that is the alpha A slash, right? In the same way, so the T, here is we can write this T, so T slash, T and T slash. This T slash can be represented plus, this is the expression plus, so T E slash, this remaining character, and this one is replace this one, that is a plus T E slash and epsilon. We can convert this grammar like this, but the here is also we can use, this is also same like. So then here is also A, alpha and beta. So in the previous case what I explained the rules. So here is also we can write T is equal to F T slash is equal to star F T slash epsilon. So but when you are replacing this statement with these two statements, and when you are replacing so this statement with these two statements, so then you can eliminate the left recursion. You can eliminate the, so this is context-free grammar after elimination of the left recursion. Have you understood that? That left recursion is also very, very important. Elimination of left recursion is also very, very important. Right? This is the left recursion of one thing. So this is the context-free grammar left recursion. Have understood that left recursion? Just you see that one more. So suppose here is the, so that is the animation is there. Just you run the slides, automatically you can get the idea about this, how to eliminate the left recursion of this. So next one is, suppose you say the left factoring. Another one is, another important thing is left factoring. So that is the leftmost derivation, rightmost derivation, ambiguity, that is the left recursion, and another one is the left factoring. Another one is the left factoring of this. Left factoring means, so that means left factor is a grammar transformation that is useful for producing grammar suitable for predictive or top-down parsers. That means the left factoring can be useful for providing the grammar for predictive or top-down parsing. For example, here is the simple thing you see that what is the left factoring means, for example, if one production having two or more products are same, then we can call it as a left factoring. For example, if statement, if expression, then statement, else statement. So then another form of this one is another rule is if expression, then statement. But when you are using that, here is in this statement, if expression, then statement, and here is also if expression, then in these two productions, these four are same. These are same. Here is the only else part is this. But when you are taking the if statement, which if it consider either this if statement or this if statement. So this is left factoring grammar. For example, you see that in the form of if we have A can have the form of alpha beta 1, alpha beta 2. Then we replace it. Suppose you see that first one is alpha is there and first is alpha. Which one you have to select? Either this one or this production. That is the ambiguity. So that means that we can call it as a left factoring of this one. The left factoring, so that means you can suppose you take this is the example if statement. If, so suppose if I taken the same thing, if means if expression, then statement, if expression, then statement, else statement and A. But in this case, here is the four letters are same, here is the four letters are then same. But when you are taking when you are trying to construct the tree, either you have to consider this tree or this tree is, so that is the confusing. So then that is the left factoring. You understand the first definition. Left factoring means, so if one non-terminal variable may be having more than one productions, if the more than one productions are having some common terminal symbols or non-terminal symbols in the sequence, so then it is called left factoring. So you see that example for each non-terminal A, find the longest prefix alpha. Find the longest prefix alpha common to two or more of its alternative. For example, longest prefix means here is 1, 2, 3, 4. These four are same. Here is 1, 2, 3, 4. These four are same. That is the length of this one is the 4, and extra we are having ES or A, right? So then suppose you take this is the grammar of this, then we can consider the left factoring of this. For example, so how to eliminate the left factoring? Left factoring is the grammar already there. So the same thing, elimination of left factoring. For example, left factoring is a grammar. So why I did not explain that means here is the animation is there. That's why I came to this slide. Okay. So don't think that I skipped that slide. No, so that is the same thing is. But here is we are taking the A can have alpha beta and alpha beta. But here is the first character, that is the prefix alpha. But here is some that this kind of expressions are called the left factoring. But here is when difficult production should be taken for expression, A can have the form A can have the alpha of A slash. A slash can be written B or B slash. We can write these two formulas. With the help of this, if the grammar is given like this, we can confirm like this. A can have the form of alpha A slash. We can write instead of that we can alpha A slash. Here is alpha A slash is, so beta by beta. So simple thing is when you are taking the common of alpha, so that is the beta by beta. This is nothing but A slash. Right? So but here is, for example, you say that context free grammar for if else statement, how that will be checking, how that will be evaluating the left factoring. For example, statement S means if statement, if I is if, E is expression, T is then, S is equal to expression. If expression, then statement. Here is also if expression, then statement, else statement. If else statement this one, and this is the if statement, and this is the other thing, that is others, and E is equal to A. So in this case, when you see that it has a left factoring. So four common are there. If the two productions are having, so four common letters, tokens, 1, 2, 3, 4, and 1, 2, 3, 4. But here is, so how do you eliminate this? So then simply you can say these two are suffering with the leftmost factoring. So but here is for elimination, you consider this S is equal to, you can write I, E, TS slash A. These you consider these as it is, and for this ES you write the slash or O. ES slash is replaced with ES and E is equal to A. But instead of writing this grammar, when you write this grammar, so we can eliminate the left factoring. We can eliminate left factoring. Have understood that? So when the left factoring comes, so if two or more productions are having the similar prefix of a specified number of characters, so then we can call it as a left factoring grammar. Understood that? So that is here is so already we have studied. But if you want to create an efficient grammar, so the C is context-free simplification. Eliminate the useless grammars and symbols. The next topic is elimination of useless grammars and symbols in the production. Elimination of useless productions. So next, elimination of unit productions. That's why if you want to increase the execution speed, you have to reduce a number of productions. So when you are reducing the number of productions, it is very easy to construct the parse tree. So by eliminating, so that is the ambiguity, left factor, left recursion like this. So elimination of useless productions. But how do we identify? This is also very, very important for GATE, because so sometimes they can give this kind of questions for this one. Suppose you see the grammar like this. For some grammar, for example, so suppose if we taken, so that is here is, so S can have the form of this one. So that is the three productions are there. Here is we are taking. So that is the three production SA, SB, or A like this. But in this case, when you are using three productions are there. But in these three productions, but in the derivation of the string, can you use these three or we cannot use? Suppose if some grammars cannot be used, so then we can remove that grammar. For example, in this case, three productions are there. SA, SB, A, SB. But here is A is a non-terminal. It will never replace. So that is the no use of getting the answer. That's why here is A is a useless symbol. Then we can remove this A and we can use only these two things. Have understood that? There is a no non-terminal symbol, only terminal A is there. But instead of using this, we can use this production. That's why it is a useless. Then we can eliminate and we can use these two. That is called elimination of the grammar, right? So consider the grammar having the following productions. Rewrite the grammar by removing all useless symbols. So that is, you think that these are taken from GATE, previous GATE question paper, right? So just you see that. Consider the grammar G having the following productions. S can have the form of A or alpha, A or epsilon. So that is, A can have the form of A, small a, capital A or A. B can have the form of B or A. But here is, what is the useless symbols? What is the useless productions here? But when you see that in the starting symbol, so we use A and epsilon, but A is nowhere related to this one. So for example, here is B is not connected to A, B is not connected to S. So that is clearly we can see that B is not reachable from the starting symbol. So suppose A is there, right? But when it comes to this, so this side A, so that is the production is A. This production is there, but here is, suppose when here is the B, this will never be reached. This is called a dead code, like the dead code elimination. Or so B can have the BA can be removed. This is considered as useless, and you can make it as good grammar. So that is only these two can be kept like this. S is equal to A of this. A means A can have the form, and here there is no B. But suppose, for example, here is also when you are taken, there is the B in this case or in this case, definitely it is the useful grammar. But here is B is no way connected to this. That's why if B tends to AB is a useless grammar. That is the elimination. This is also very, very important. You see that S can have the form of A or epsilon. A can have the production of A can have A, small a, A. But B no way used in the solving of getting this thing. That's why we can call it as a string. And here is this is the simplified grammar of this one. S can have the form of A epsilon. A tends to A comma A like this. So second one is eliminate all the useless symbols from the grammar G given by the productions. So that is elimination. So how do you eliminate this? First you see that solution. Is there any first thing you see that is there any grammars, any useless grammars or not, which are not using? Suppose consider C is equal to A, C or B. So C is there. You can see that there is no termination for this C. Here is a C, but when you are using the C, but C is connected to S, but when you are using the C, C is always replacing with another capital non-terminal symbol. So, but it is not terminated, right? There is no epsilon. So that's why here is we can remove the production. C can have the form A, C, B can be removed, and here is A can be, C can be removed. So that after removing the C productions, we get S is equal to A, S or A. Just remember, are you following? Yeah. So that is A, S or A or C. Then here you see productions are removing. Then we are getting S is equal to A, S is a B of this one. So next again you see that S A of A. So that is the B is no way connected to S. B is no way connected to S. So that's why we can remove this production of B also. We can remove the B. So that is the finally. So when you are given that S can have the form of AS or A. A can have form of A. So that means here is you can see this. So this entire grammar, when you are given this grammar, first you have to eliminate to construct the efficient parse tree. Then here is only you got two productions. What are those? These two are okay. So these two are eliminated, useless, and this C is also eliminated. So that is the third grammar is given in productions. The same thing, S is equal to ACB, C is equal to ACB or F. Find the language generated by the grammar and also rewrite the grammar by eliminating epsilon production. But here is, but actually suppose in the DFA, you have to remove the epsilon. So if you want to remove the epsilon and you have to rewrite another grammar. So that is, you write in the another form of this one. So for example, you see this, when you see the grammar, when you are replacing that, it is fallen infinite. That is the infinite case you can get. Suppose S is equal to ACB. Again C is equal to ACB. That means always you can get values of AB, 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 AB up to N values you can get. So that is the so suppose here you see that in this grammar, always you can get A, B, A, B, dash dash up to N. So this is the infinite. But when you are taking that according to this rule, so that is we have studied about that. So you can get A to the power of N, L is equal to A to the power of N, B to the power of N, such that N greater than or equal to 1. So this producing the language AB, 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 AB up to N. So that is the infinite times. So here is also, so but when you are replacing that C, so that is the C is always replacing AB, 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 AB like this. So then here is you can get the grammar is like this. So here is this grammar is we can eliminate. So by epsilon can be eliminated by using AB and AB. So that is infinite, no? So epsilon can be replaced with AB and AB. So then here is, in this prediction, we remove this epsilon and we are keeping the values of this one. So this is the elimination product of this one. Suppose for example, so here is the, whenever we are using that, this is the elimination of this grammar. After eliminating that, so epsilon is replaced with AB, AB, and here is also we are using, we have to eliminate the epsilon. Right? Have understood that? how to simplify the grammar. So for example, eliminate the unit productions from the grammar, given grammar for the following. So this is the last one. After that I will explain the gate questions. So S is equal to AB, A is equal to A, B is equal to CRB. So C can have the form of D can have the form of E can have the form of this one. That means here is most of the cases we are repeating. Blindly we are writing the productions. So that is how many productions? 1, 2, 3, 4, 5, 6 productions. But if these unit productions, then no use. D is equal to E. So D is a non-terminal and E is a non-terminal. So that is no production will be, no output will generate. C can have the form of D. C is a non-terminal and D is also non-terminal. So that is they cannot have any use. So here is the B can have the form of C or B can have the form of B. So then B can have the capital C, that is also unit production. So then it is also not useful. That's why these are unit productions. B can have C, C can D, and these are the useless and these are the useful. But how to eliminate this means, for example, you see that D equal to E. So E is equal to A. So that's why, so you can remove that. So A is replacing, then D is equal to A. And again you can use the C is equal to D, D is equal to A. B is equal to C, C is equal to A. So then here is according to this rule. So then after eliminating, we can get the productions like this. Yes, AB, A tends to A, B are this one. So these are the problems we have studied. Now we'll solve some gate problems. There is only 5-10 problems are there. Only that is 20 minutes is there. So what we have studied up to now. So first, what is the syntax analyzer? So that is what is the context-free grammar? So that is the construction of parse tree. So that is the leftmost derivation, rightmost derivation, ambiguous grammar, elimination of the ambiguous grammar. So that is the left recursion, elimination of left recursion. So left factoring grammar, elimination of left factoring grammar. After that, elimination of useless productions. So that is the unit productions and the useless symbols, right? So this chapter is very, very important, right? So whatever I explained, so you should be thorough. Definitely you can get one question from that. Minimum of one question you can get. So from this, I understood that. Now, so on the same, this is the parse syntax tree. So I had given some gate problems. Just you see that the first one. So that is in the 2014 you got this question. So consider the grammar defined by the following production rules. Following production rules with two operators. So you see that two operator plus and minus, plus and star and plus. The productions are given. S can have the form of T star P. T can have the form of U or T star U, and P can have the form of Q plus P or Q. Q can have the form of I comma. So that is U can have the form of ID. So which one of the following is true for this one? Just you understand the question. Consider the grammar definition by the following rules. This is the grammar, and here is just you see that 4 options here given. What is the answer? Here is the plus is a left recursive, and while star is a right recursive. Second, B, plus is a right associative, and while star is a left associative. Both A and B are the right associative, or both plus and star are the left associative. So most of the cases, here there is a one confusion is there. Even that is the intelligent student also, so he might be confused. Why? Because what is the question here? So both are having right associative or both are having left associative. So that means evaluation should be from left to right. Left to right means the plus and star also executing from left to right. But here is, but this is not the correct answer. But here is what he has given. So that is plus is the right associative and whilst is the recessive. Because here is associative means how that will be evaluating. Either it will be evaluating in the left recursion, leftmost derivation or rightmost derivation like this. For this one, but B is a correct. For example, you see that plus is a right associative. When you see that operators, here is a plus. In the plus, P can have the form of Q plus P. That means the production P will be having right side of the P. Right side of the right side of the plus. P is having right side of P. So then it will be right associative. That will be, so the expression will be evaluated from right. Right is the rightmost derivation like that. Right will be expression. So that is the plus is the right associative. While star is, suppose when you see that T star T, but here is you use this. T can have the form of U slash T star T. So T is before the star. T is before the star means, so that is the expansion of T productions will be in the left side. The expansion of T productions will be in the left side. That's why, so the star is a left associative and plus is a right associative. But you consider this grammar, then only for this grammar only, so that is the plus is a right associative and star is a left associative. But in the C program, when they ask, so you have to say that that is a left associative. So only for particular grammar, plus and star. So that's why B is the answer. But most of the cases, the students will confuse about this. So they are giving, so that is the answer is D. Both plus and star are left associative. They are giving this question. That's why, so they are thinking that, so that is both are associated. No, this is wrong. But the answer is B. Here is when you are taking, so that is answer is B. B is correct answer. Have understood that? So second question, you see that second, the grammar A can have the form of capital A or within the bracket capital A or epsilon is not suitable for predictive parsing because the grammar is predictive parsers. Generally, the predictive parsers, that is the top-down parsers, does not allow left recursion, right recursion, ambiguous grammar or left factoring. So if the grammar is having any kind of these things, so definitely it is not possible to draw the, so that is the top-down parsers. So that's why you have to eliminate this. But here is the grammar as given, so why it is not suitable for leftmost grammar. For example, you see that we are using this grammar in 2005 they got, so they got question in 2005. A can have the form of A or A epsilon. So that is all A's are there. This is, so suppose for this A, so epsilon is there. For this epsilon, so that maybe you can get any number of trees. So then this grammar is ambiguous. This grammar is ambiguous. This grammar is ambiguous. Left recursive, so that means it will be having the first character is this, that will be having the left recursive and right recursive. So then here is this, so that is the right most derivative. This here is when you are using this with the left recursive or this may be the right recursive. But anyhow, so this is the ambiguous grammar. This is ambiguous grammar. So even it will be having that ambiguous means these two will be also included into this. It is not it is not left recursion, it is not right recursion. But here is when you are using this, so that will be fallen infinitely, right? Epsilon, 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 epsilon. So that means here is recursion will not be comes like this left recursion or sometimes. But answer is ambiguous grammar. It is a ambiguous. Ambiguous means, so more than one parse trees we can construct with the help of this A. Suppose when you are taking this production, so suppose A, epsilon, epsilon, epsilon. Here is also we can take epsilon, epsilon. Here is also we can take epsilon, epsilon, epsilon. So that is the grammar is more than one trees we can construct. So that's why it is a ambiguous grammar. So consider the grammar. Third question. Consider the grammar. E can have the form of E plus N or E into N or N. for the sentence n plus n into n. That is, in the previous case already was id plus id into id. The handle is the right sentential form of the production. That means this is the rightmost grammar. So in that cases, which one is the correct answer? Suppose if you want to get this rightmost thing means, suppose here is, so first you take this one. Rightmost means from the right side you have to start it. Suppose here is E and N is there. But here is N is there. Suppose here is, you can draw the syntax tree of this one. We can write the follow E plus N, and E can have the form of this like this E star. So that is here is, for example, you can take that is the E. So this can be having either star or multiplication. So first one is, here is the first plus is there. So that's why, so that is the second. Rightmost means first we can consider these two. So then here is this expression we can write. So that is the E star N, E star N, and here is after that E is replaced with, so suppose N is there, E can be having the plus. Suppose if you want to replace this, so E can have the form of E, that is the E plus N, and E can be replaced with N. So then this is the value of this one. But here is, when you see that the D is the correct answer. So first B is the correct answer. First we are taking this is the E into N we are taken, right? So after that E plus N we are considering this. That's why it is the D is the correct answer of this one. So fourth one, GATE 1999. Which of the following is essential for converting an infix expression to postfix from the efficiency? So in the stacks we have studied infix expression, evaluation of postfix expression, conversion from infix to postfix, conversion from infix to prefix notations, right? So because in some languages we can use the intermediate form is prefix notation, but in the most of the languages the intermediate form is the postfix notation. So according to that, which of the following is essential for covering an infix expression to the postfix from the efficiency? So that is, here is an operator stack, an operand stack, an operand stack, and operator stack are parse tree. So which one is the correct answer? So but here is infix to postfix expression. No? First, when you are converting that infix to postfix, that is the postfix expression. So here is, so generally the operator stack, that is the operator stack is the answer. A is answer. So then the operator stack can be used for converting infix expression to postfix expression, and operand stack is, so that is used to convert infix expression to prefix notation, prefix thing. So that means an operator stack, suppose in the data structure already we have studied this, an operator stack can be used. So in the input, so that is the for conversion of postfix, and the operator stack is used for converting infix to prefix notation. So that is that one. That means it is not this one. It is not both. Or they not a parse tree that can be used different. That's why answer is A. For this one, you can say that answer is A. Answer that. So that is context-free grammar is ambiguous if. So that is the context grammar is ambiguous. Ambiguity means if that is the same sentence, having more than one derivations, that is called ambiguous. It has more than one rightmost trees, or it has more than one leftmost tree. No parse tree can be generated for the context-free grammar, or A or B. General definition for ambiguity is, if the expression having the more than one derivations, then that is called ambiguous. Here is a more than one right derivation, it is ambiguous. More than one left derivation is also ambiguous. So more than one tree, either left or right, that is also ambiguous. So that's why, so D is the answer. So suppose here is, so we are saying D is answer. So because A or B, so that is again A, sorry, A and B. So that is here is, so that is the both are correct. A and B both are, so that my answer is D. So that is the answer is D. Fifth one. And the sixth one. Which of the following are always unambiguous? Which of the following are always unambiguous? Deterministic context-free grammar, non-deterministic regular grammar, context-sensitive grammars, or none of the mentioned. So which one is the always unambiguous? So in the previous class already I explained. In the implementation of tokens of lexical analyzers. So that is, here is the deterministic context-free grammar. Non-deterministic means for given input values it will reaches to more than one states. So not constant. So that means here is the deterministic is the deterministic context-free grammar is. So that is the answer for this. This is always unambiguous. That means for any given input symbol it goes to only one state. So that's why here is A is the correct answer. Seventh one, a context-free grammar is not closed under iterations. That means dot operations you can perform in the bottom of parsers, union operators or concatenations, but here is iterations, that is we cannot use the closure of that iteration. That is the answer is D. Is not closure under iterations. Is not closure under iterations. Eighth one, which of the following is an example of inherent ambiguous grammar? Inherent ambiguous grammar. So that is the eighth question. Here is the a to the power of n such that n greater than 1. So that is the a to the power of n, b to the power of m, c to the power of m, and n comma n greater than or equal to 0. But when you are using that, for this b, we can have any number of trees. But here is we are having the a means only we can use the any number of a's directly we can give. But here is inherent means from the, so parents it can be find the ambiguity of this. That's why. So answer B is ambiguous. So state true or false. Statement R is equal, R can have the form of R or T, where T is epsilon. Is an ambiguous grammar or not? You see that it's a very simple question. It's the last one and a very simple question. You can answer for this. State true or false. Here the statement is R can have the form of R or T. T can have the form of epsilon. Is an ambiguous grammar or not? Yes, it is always ambiguous grammar. It is always ambiguous grammar. But for this epsilon value, suppose when you are taken, so that you can have the productions, you can have either itself or empty string. That is empty string means we can convert any kind of things. That is true. Answer is true for this, right? So that is this is the today's class. I hope you understand. So this chapter is a very important for GATE. So that is the syntax tree. So the syntax analysis is a very important. So that's why in the next class I will explain a top-down procedure, top-down parsers. After that, in the two classes I will explain the bottom-up parsers. So I have understood that. So that is, if you have any queries, you can post. So that is, so today I am stopping my class. So if there are any doubts, you can ask. So thank you for your patience. Thanks for listening my lecture. And so that is based on my lecture, you can give the comments also. So no problem. So that is so that I can improve. So thank you for giving this opportunity. In the next class, I will explain. So top-down parsers. So thank you.